Okay, welcome everybody. Welcome on in. So getting started, we have what today? We've got the 18-week full semester statistics class, moving ahead with things, and getting into what I think is one of the more interesting topics of the course myself. I find it enjoyable to sort of examine it. I think it's a little more interesting than a hypothesis test or something like that. And also, I think it's a little more accessible to students. If you take the time to really, like some of it's pretty basic and students pick up the basic pieces. But if you take the time to really dig into what's going on underneath, you can really get into some interesting stuff and you can get into these interesting types of scenarios. So I'll be expanding on correlation today. We've talked somewhat about correlation. So some of the stuff I've said, you go, oh, I think I've heard him say that before. Yeah, you'll hear me repeat some of the stuff because I'm setting the stage to really set up what we're really talking about today and what I think is a fairly interesting portion of the course. Do notice you have two due dates coming up. October 10th, your survey question summary. We talked about that last time, and your project visuals. So be getting those ready. Do try to make sure you use the labeling well. Remember, in the inside of StatCrunch, you've got your X label, Y label, and your title. Make sure that you really should be using all three of those. So when you go back to your visuals, I can sort of show you. So let's say if we go into here, say I want to make a histogram. Like this is one of those things that's easy to do and is definitely worth the points because if you don't do it, it's eye-catching. Like a person notices and go, well, why didn't they do this, right? So let's say you've got a histogram. We want to do height. You can mess around with your bins here. Certainly want to do that. And then right here, X label, Y label, title. All three of those should be filled in, right? That's like the first red flag to communicate to people that you don't really know what you're doing is you do not have a well-labeled visual. Yet a really well-done visual communicates the opposite. It communicates to people, oh, this person knows what they're doing. Look, they have units in there and they've described everything. This is a really well done graph. I think maybe this person knows what they're talking about. So that's one of those things that's really easy to do. You just come in here, look for these three things. If all three of those aren't filled in with the proper information, go change it, right? That's like one of the easiest things that you can do. Put the title in here and then put the unit, just like I have my title here for the column, shoe size, United States. So I could put that. Which one did I pick? I picked height in inches, right? That's the one I chose here. So, my x-axis would be height in inches. I would give both what it is and the unit. Give the whole thing a title. Just, you don't have to repeat what's already in the x-axis and y-axis labels, but just give it some kind of a title that lets people know what it is you're working on, right? And then the Y label for a histogram is usually the frequency. So you could either leave that as frequency or, put count or something in there to just make sure that people realize, oh, that's the count. That's what we're doing. So we might make this, so for instance, if you were going to measure, what would this height? If we're going to measure height, you probably would separate men and women, right? Because men are in general taller than women. Like the mean and median height for women is shorter than the mean and median height for men in most circumstances. So men are just a little bit taller. So, you might put in here, you'd go frequency for the y-axis. For my x-axis, I could put height in inches. And then for my title, it would just be a little more specific about what was the point of what we studied here. So this could be like American men heights. So notice how my X label, sometimes there's a tendency to confuse the X-axis label and the title. Notice how they don't really overlap. This is telling us, oh, this was done in America and they looked at men's heights. But then when I look at the x-axis, it's very specific. This represents the height, and it's in inches. So now when I compute, look what I got there. Really good-looking graph, right? My x-axis is right. If you go in here and this still says like Q4 or Q7 or Q34 or something like that, just go in and change it. It's a little bit of polish that makes it, first of all, it makes a much better graph, but also it really makes it look like, oh, this person really like knew everything to do to make this graph look good, right? So we've got that, and then of course I can go in. If we look at right now, my looks like my width of my bins is 1. I could just go in and play around with that and go, what if my width was 2? What would that look like? Oh, that's not as good. That doesn't give me as much information. I'm going to go back and make it 1 again. But see how easy it was to just try a couple things and see? And then I'm right back to my graph that I had before. Okay? Yeah, so keep that in mind because you're all going to be doing this because you've got your survey questions summary, which is pretty easy. You just use remember, you go in, you do the summary stats, columns, pick your column, compute, and you've got all sorts of stuff here. Your mean, median. You could even just take a screenshot of this and then save it in your folder for later or whatever you want to do, right? Create a whole new stat crunch and save it. However you want to do it, whatever works for you, okay? But you've got those 2 to do. Whoops, what am I looking at? These 2 to do coming up. Let's see, the 13th. I probably see you again before the project visuals, but hopefully people will be turning these in over the weekend and getting ready for that. Okay, so don't miss those dates. Make sure you know about that and that you're ready to go there. Okay. Oops, I didn't greet anyone in YouTube today. Let's go ahead and let's see. What's a good greeting? Hello. Hey, everybody. And then also I'm going to put, I put this in there last time, but it's this is just sort of an example so you can see. This is a link of how to do part of what we're talking about today. So if you want a nice, quick, clean video where this individual goes through and shows you how to do for not the parts that are due right away, but what we're talking about now, correlation, you will be able to do that. So here's your link. And again, anytime you're stuck in StatCrunch, just go into, either directly into YouTube or if you want, go on Google, either one, right? It's the number 1 and 2 search engines in the world. Go in there and just put what it is that you're looking for. So StatCrunch correlation or StatCrunch histogram or StatCrunch regression, whatever it is that you're trying to do, and you're going to get a bunch of really great videos that are nice, short, quick things that just show you how to go in there and get what it is that you're trying to get, just like this, okay? So don't be afraid of the search engines. That's not cheating. That's you trying to get some help with how to fix your stuff, okay? So let's see, where are we? So we're getting into scatter plots, diagrams, correlation. So I talked a little bit about this before. Remember, there's this, so some of this will sound familiar, and hopefully some of you have started Chapter 4 and are working through it. There's a tendency that anytime things are related to think one causes the other. Our brains just naturally do that. You just listen to the news, you hear people do this constantly, politics, any of this. People will draw a connection and they instantly say, well, then this thing causes this, right? So they can, whatever it is, their point of view that they're trying to get across. But usually in life, things are not that simple, right? Like look at like one thing that I remember was a particular conversation that I heard on the radio one time when I lived up in Washington. They were talking about illiteracy rates. So that is people who, people who can't read, basically. So people who are at an age that you would expect people to be able to read but can't, right? And so there was this argument on the radio. They were all arguing about the reasons that we still have people that are illiterate in this country and don't have they don't read at grade level like you would expect them to, and they were arguing over what the cause was, right? And they were sort of in this mindset that there could only be one cause. No, the thing I'm arguing about, that's the reason why there's illiteracy. And then people on the other side were like, no, this other thing is the reason why there's illiteracy. And it's and the reality is they're probably all right. All of these things contribute to illiteracy, right? The fact that we have, schools in this country are very, very uneven, right? depending on your address when you're born, kind of dictates the type of school you'll go to and the level of quality of that school. Some people end up going to schools that aren't as good, and it makes sense. Your reading comprehension is not going to be as good, right? Some people have homes where parents are working so much they're not really at home to be able to help their children learn to read and stuff like that, because they're out trying to make sure that they can pay rent and stuff like that. So it's one of those situations where it's messy, right? When you stop and look at it, there's more than one thing that causes illiteracy, but there are lots of things that we can see are correlated. So, one thing to remember, I don't think he did it in this edition, but they usually put in here in big letters, correlation is not causation. In other words, just because we can show two things are related does not mean that that is the 100% cause of that effect, right? Because there's probably multiple causes. And sometimes things are related in a way that isn't even close to cause and effect. We talked about this with ice creams and shark attacks. Definitely correlated. When one of those goes up, so does the other one. But obviously one is in no way causing the other. They are both effects of a different number of causes, namely heat. When it's hot, ice cream consumption goes up, so do shark attacks, because then people go to the beach and get in the water and stuff like that. But in no way is one of those causing the other. There's these other variables that are there contributing. So you have to be in that mindset when you're talking about correlation and regression, which is, this is not the sole cause, but there is an effect, right? And what statistics could do, that conversation I was talking about a little while ago where they were talking about illiteracy, statistics has the tools to dive in, and they could put a percentage on those topics that people were arguing about, but those people didn't know statistics and the audience didn't really know statistics. Which is another one of those cases where people go, oh, when am I ever going to use math? Well, you won't use it if you don't know it, right? But the people in that conversation could have done some statistics and said, yes, this thing that I'm trying to say is the cause, that's actually 30% of the cause of illiteracy. And then the person across the table could say, yes, and statistics shows that my cause is 27% of the cause of illiteracy. And then we could all look, we could sort of realize, oh, these are all problems, right? The fact that some schools are just not as good as others, yeah, that's a major contributing factor to people not being able to have as good an education. Also, the fact that we have extreme inequality in the country, that's a contributing factor. These are all things that we could sort of work on to try to make sure that, if we really care that everyone's able to read, then we should be able to scientifically try to find those causes and look at them, rather than just making it like a political argument back and forth where we're just trying to win an argument. We can use statistics to dig down and try to actually find the causes and come up with some solutions. But you rarely see that in a public forum. It's most of the time it's more about the drama of arguing than it is about getting to the bottom of things. But so we have this correlation coefficient R. That R is a measurement that tells you how closely are these two things affected. Now, again, that does not mean cause and effect. Even if you have an R value that shows that two variables are very closely aligned, that does not mean cause and effect. So remember, we have this scale from 1 to -1. If your R value is close to 1, you have a strong positive correlation, meaning the two variables go up together, pretty much together. If it's a strong negative correlation, that's still a strong correlation. It just means things go the opposite direction, right? It doesn't mean they're not correlated. It means as one thing goes up, the other goes down, but they still are very much affected. If I move one thing up, the other one has to move down, right? Think of like, I think the example I gave last time was a volume in a speaker. As you increase your distance from the speaker, the volume goes down. They are still very strongly correlated, but the correlation is in opposite directions. So then what is in the middle when you're close to 0, when you get an R value close to 0? That means the variables don't really affect each other, right? So that would be like your distance from the speaker and how hungry you are. Well, the further, and if I change my distance from a speaker, that's not going to affect how long it's been since I've eaten, right? So that would be very small. We would expect to see basically no correlation, pretty close to 0 for that R value. So sometimes people get confused with that. Like they get the part near negative by 1 where they say, oh yeah, the two variables go up together. But then they think at -1 that they'll go, oh, there's no correlation. There is a correlation. It's just an inverse relation. As one goes up, it causes the other thing. I shouldn't use the word cause. As one variable goes up, the other variable goes down, the opposite direction. It's in the middle zone, like near 0. That's where things don't have anything to do with each other. It's like just variables that are not related. Okay, so it's kind of a weird, for some people, that's kind of a weird scale to think about a little bit. So lucky for us, we have technology that's going to give us this R value, right? If we were in the classroom, many of you would have a TI-84 because the school provides them and they're handy to have in the classroom when they're trying to do statistics. It spits out an R value for you, right? No, remember, your R value always has to be between -1 and +1. So this would be a pretty weak, this R value is pretty weak, 0.59. That's not really very close to 1. So this would be a very weak correlation. One variable could move a lot and not really affect the other one very much. You always want to know that R value. If you are talking about correlation and you're talking about regression, you're doing anything there, you need to have calculated that R value. And it's easy. The StatCrunch does it for you. But you need to know what that is. Okay? And I'll show you how to do that in a little bit. That video I posted will show you how to do that as well. It shows you how to do a whole bunch of stuff that you need. So they go through, they calculate the R value by hand. Good news, you don't have to do that, right? You're not going to have to calculate the R value by hand. Here's that range I was talking about, right? You've got 1 and you've got -1. Notice how they say in this range you do have a correlation, and over here you do have a correlation, and in the middle no correlation. Remember, that's arbitrary. This cutoff point of 0.878, that's just an arbitrary value. If you come in with an R value of 0.876, it doesn't mean you should throw it away. Like maybe you still want to argue that there's a decent R value, that there's somewhat of a correlation, but it's maybe a little bit weaker. It's not an overwhelming correlation that we're dealing with, right? So like most things in statistics, these cutoff points are, they're good rules of thumb, but it doesn't mean that they're written in stone, and by if you ever get an R value smaller than this, that you should just throw everything away. There's no connection. You have to sort of play it by context, whatever problem it is that you're working on, right? But the closer you get to 0 from either direction, the weaker your correlation is. That implies that our variables are not really related in any way. But again, even when you get close to 1, that's not saying cause and effect. I'll hear cause and effect in projects when I'm watching the videos. It's not cause and effect. Okay, it's just related. Right, where am I? Interpreting R value. Right. And here that R, you'll see that R squared value pop up. I'm not gonna worry too much about the R squared. I think it might come up in the homework a little bit, but here's the idea. The value of R squared is the proportion of the variation in Y that is explained by the linear relationship between X and Y. So remember I talked about earlier how we can pin down, well, this is 37% of the problem with illiteracy. This is 40% of the problem with illiteracy. That's what you'd be using as your R squareds to do that kind of example. Right, so we see that here. Here's a problem, an R value of 0.813 and R squared is 0.661. So they say we can conclude that about 66% of the variation in height can be explained by the linear relationship between length of shoe prints and heights. Right, so that means there's 34% left over. So that's why you always have to be thinking about that there's, there's more than one thing usually that causes something. If something was so simple as to be just a straight up cause and effect relationship, we don't need statistics for that. You just see it occur. I punched the wall. Now there's a hole in the wall. There's nothing to study, right? There's nothing to wonder like, I wonder how that hole got there. Well, I just punched the wall. That's why there's a hole in it. So therefore, there's the whole situation is understood. You don't need to bring statistics in. All right, some common errors involving correlation. So, like I mentioned, a common error is to assume that correlation implies causality. It does not. Okay, we cannot make the claim that this thing is the sole cause of this other thing. It's more like an effect, right? Like imagine you have say you live in a house with a sibling, right? Well, the decisions your parents make, like affect both of you and your sibling, right? So at the same time, you and your sibling might both be hungry because no one's made dinner. But it wasn't your hunger that caused your sibling's hunger, and it wasn't their hunger that caused yours. There was another variable, i.e. when your parents made dinner, that caused both of your hunger. That's what we call a lurking variable. It's that other piece that isn't part of your equation. Sometimes the lurking variable, doesn't take very long to find. Sometimes it's really hard to find. One example I gave earlier in the course was you can tie the number of vehicles that a person owns to life expectancy. Neither one of those things is causing the other. The lurking variable in that case is wealth, basically. How much money do you have? People with lots of money have better and more vehicles. People with lots of money have better health care and live longer. So that's the lurking variable there. Oh, right. The other thing is people kind of think about this linear regression. The most common type of regression and correlation that you're going to hear about in statistics is linear correlation, but it's not the only kind. So sometimes people might just be dealing with correlation and go, well, I'm getting kind of weird values. What's going on? There may be a correlation, but it may be another type of graph. Right? Remember all the different types of graphs you learned in algebra? Lines are super important in mathematics. They come up in calculus and stats and all sorts of stuff. But there's other functions out there. There's exponential functions, quadratic functions, all sorts of stuff. The relationship that describes the variables you're looking at might be one of those other types of functions, right? So just be aware of that. We haven't got to hypothesis testing yet, so we won't talk about that. I thought there was a graph coming up that I wanted to look at. Somewhere in here there is. All right, so here's the one that I use a lot. We've got shoe size and height, right? So you could kind of, if I told you to draw a line through this data, you could probably kind of come up with one, right? You could sort of see where it goes. Our software is going to spit out a bunch of information for us, and we want to be able to interpret that. So let's see. Is this the part where I want to do I think so. I think I'm to the part where I want to show you StatCrunch. Okay, so yeah, almost. So regression. What is a regression? This goes by a bunch of names. They're all the same name. Right, so you know how someone and like their parents call them one thing and their friends call them another thing, and then people who don't know them really well call them like maybe their like official name or something. So the one person, but they go by like 3 or 4 different names depending on who's talking to them. Maybe their significant other calls them another special name or something. So they have all these different names, but it really means the same thing. It's still the same person. Regression line is like that. You can call it the regression line. You can call it the line of best fit. You can call it the least squares line or the least squares regression line. The thing has like 6 different names. But what is the regression line? The regression line is a scientifically calculated line. So it's created by formulas, which you won't have to use in this class. But it's not like we just sort of come up with a line that looks good. You come up with a line, and that line is like a model. So remember in mathematics, what a model is we take a real-life situation and we come up with a mathematical construct, either an equation or a function or something that acts like that real-world situation, right? So that's what a regression line is we're coming up with a line that acts like the data, okay? Now, statisticians kind of want to do their own thing. They make this a little bit complicated. This looks like, oh, what is it? What are all these symbols? Let me blow this up a little bit. What's going on here? You learned this back in beginning algebra, right? Some of you maybe earlier. This is just your y equals mx plus b. Usually people remember y equals mx plus b even if they can't remember what it stands for. But in stats, they like to write it differently just so that they kind of have their own thing going on. This is just your y value, so it's y hat, but it's just the y value. Equals b0, that's just a number, so that's like your b in y equals mx plus b. And then here we have b1x. That's just your mx part. So this is really just the equation of a line. Y equals mx plus b, slope-intercept form. So b1 gives you your slope. Now let's remember, there was another name, another way we interpreted slope back when you were learning lines. That was the rate of change. This is really good. If we can come up with a line that fits our data that tells us our rate of change, that gives us a pretty good ability to make predictions about stuff, right? Now, your predictions aren't going to be perfect, but they will be approximate, and they should be, depending on the better correlation you have, the more predictive your line is going to be. But you could predict values that are sort of missing values, unknown values, and you could calculate the expected value, what you could expect from that. Excuse me. Always get the hiccups in the morning when I talk this much. B0 is our y-intercept. Okay, and then y is just our y. So in other words, this actually gives us a tool that allows us to make predictions. So that regression line is really great, and it looks kind of cool when you put your regression line over your data. You're able to visually get a sense of how well your data fits that line, or how well that line fits your data, I should say. So you have two things you should always look for when you're doing a regression. You should look at the R value, and then you should look at your scatter plot with the line on it. Both of those need to be examined. If you just do one or the other, sometimes an error is going to slip through, right? You pretty much always need to calculate the regression because it's hard to eyeball what your R value would be. But there are some things that have a high R value that when you graph them, you go, oh, something's wrong here. I don't want to use this value. Okay, so you should always look at both. And let's see, we should see an example here. Where are we? Here we go. So here we have that shoe size data again, right? And we have a line kind of going through the data. So this represents things pretty good. Looks like once we get up here, the heights start to get a little bit variable. This person has a large shoe size but is not very tall. This person has a smaller shoe size but is much taller. But see, this line is our prediction. If we were to predict, what about right here, say 30.5? Well, it would give us a prediction of a height of this person right here. Now, that doesn't mean that person will exactly be that height, but it gives us a ballpark of what we can expect that person to be roughly. Okay, we're making predictions. If we could predict things perfectly, that we could tell the future. We can't do that, but it's good to get a nice estimate. I thought there was a better graph in here. Let me see. Oh, here we go. Before we do a few more. So here's a better one, right, with more data points. So we see the data kind of spread out, and we've got our line going through there. So you can go, okay, yeah, that line kind of gives the overall shape of this. But we can see it's a little bit of a loose, a loose correlation. It's not super tight. The points aren't all super close. But look at this regression that we get. Y equals 80.9 plus 322x. Remember, this is our slope. 3.22 is our slope. That's telling us the rate of change. In other words, as x increases or decreases, that's telling us how much our y should change. So as x goes up 1, so as the centimeter of the shoe length goes up 1 centimeter for x, that means the height should go up 3.22 centimeters. So we can make a prediction. If we're missing a value, like right here, we could make a prediction and say, what happens at 33? Plug 33 into this equation. Your y value is the height that you would expect a person whose shoe size is 33 centimeters, we can predict the height we would expect them to have. Are we going to be exactly right? No. Are we going to be roughly in the ballpark? Probably. Most of the time you will be. So that can be helpful. So don't forget that, we kind of always were telling you when you were doing slopes of lines back in beginning algebra, the slope is the rate of change. Well, this is the use of that. There's lots of uses of it, but this is one use of that where you're actually going to put that into use, and it helps you gain understanding. It's helping you gain an understanding of the connection between shoe size and height. Oh, we expect that as you go up a shoe size, we expect you to be about 3.22 centimeters taller. Or as you go up a centimeter in shoe size, we expect you to be 3.22 inches taller, right? That's that kind of that's how we expect that to work out. Now this is what we need to also discuss. In a scatter plot, an outlier is a point lying far away from the other data points. Remember, we have these loose definitions and then stricter definitions of outliers. But remember, an outlier is a data point that's like far away from your other data. Okay. With regressions, outliers, the more extreme they are, can start to mess things up significantly. If you have one extreme outlier, it can throw your whole regression line off. Okay. So paired sample data may include one or more influential points, which are points that strongly affect the graph of the regression line. So you think of it as like a weight on the end of your line. The bigger that weight is, it's going to like tilt your line, right? Your line's going to tilt. That can happen. So see how we've got So let's see, is this the one? Yeah, with one additional point. So see the difference between these two graphs right here? This is here. They add one extreme outlier, and look, the whole graph, instead of being this slanted line, now becomes almost horizontal. Because this piece was so extreme, it's so far away, it's like putting a big weight on the end, and it just like pulls this end down. That's what this point is doing, is it's pulling this end down. So when you're doing a correlation or regression, if you have an extreme outlier, then your whole regression may fall apart, okay? And you may have to throw it out. It's another one of the reasons why you look at the R value and the picture. If you just look at the R value, you're never going to notice that you have this outlier out here. But if you look at the graph, you go, oh, this is really kind of throwing everything off here. Maybe this is not as good. So we have these things called residuals, right? And we'll deal with residuals a bit. What a residual is notice how in our graph here, let's look at this one over here. Notice how some of the points look like they're kind of right on the line. Some of the points are really close, but most of the points are a little bit distant from our line. The distance of this point, the vertical distance from the point to the line, is what we call a residual. It's basically the error between the predicted value of that point and the actual data value for that point. That's called a residual. So when you start hearing residuals, that's what that means. It's the observed y, that's our data point, minus the predicted y, that's the one given by the regression line. So the difference between those is essentially an error. We call that a residual. Now, a lot of times when we use the word error, people go, oh, that means we made a mistake. No, we didn't make a mistake. What it means is that our predictions are not perfect, right? We can't actually tell the future using these kinds of tools, but what we can do is come up with really good estimates for what we think the future is going to be, or in this case, an unknown value. We can't really know the unknown, but we can make predictions. But you also would expect those predictions are not going to be perfect. So see how it's these vertical distances between the actual value and the line. Those are called residuals, right? And we end up squaring the residuals for, we kind of get into a little bit of the nitty gritty. You don't necessarily need to know for this. It might come up a little bit in the homework. If you add up all your residuals for a least squares line, or if you add up all your residuals, they add up to 0 generally. So that's a problem because then with the number 0, we can't find anything out. That's why they use the square of the residual, because then everything becomes positive and they don't cancel each other out. So when it's called a least squares regression, that's what they're talking about. They take the residual, square it, and then add those together, because if you just add the residuals, they all cancel each other out. Okay. And then they're just kind of getting into how this comes about. So I think that was all I wanted. Oh. So this is something that's a little bit fancier. I probably wouldn't expect you to do this in your actual project, but you are welcome to. It would be impressive if you did. And it's not that hard to do. But we can actually graph the residuals. So remember, the residual is the distance from a data point. It's vertical distance to the actual line, the actual regression line. If we plot those residuals, you really should see something like this. That is just a random pattern. Like when I look at this, I don't see like there's not a pattern, there's not an overall shape. It's just they're kind of all over the place. That's an indication that your regression is probably a good one. See how here we could describe a pattern here. Well, our residuals go down, and then they're decreasing, and then they start to increase again up to a point, and then they start to decrease down again. There's an overall behavior. What that means is your line is probably missing the actual shape of the data. It might have a decent R value, but it's missing it. Same over here. We can see an actual pattern. Oh, it looks like the distances for each one, they're alternating up and down, and then, but they're getting bigger and bigger. Those residuals are getting bigger and bigger each time. If we can describe that overall pattern, it may indicate that there is a correlation, but it's not linear. It could be exponential or quadratic or something like that, right? So, but we're not going to get into that too much. I think that's the last of what I wanted to say there. Let me just double check real quick, but I think we're ready to jump over to StatCrunch. I can get through here. Let's do it this way. There we go. Rank correlation. Yeah, okay. We're not going to worry about that. Okay, so here I've got some values, right? You'll have this. You should have, this is the reason that I had you do at least 2 quantitative questions so that you could make a scatter plot and you could do a regression. Okay, and we'll see what your conclusions are. Some of you are going to have conclusions where you go, yeah, these variables have a very low R value. They don't seem to be related. Some of you are going to have R values that are high and do imply a correlation, right? It'll be kind of interesting to see some of these. Some of you that did like number of hours worked versus number of units taken in school, something like that. I'd be interested to see what you come up with for your scatter plots. And your line of regression. So what you do here is you go, now I have to remember, I just watched it, but we've got, oh, right. So you go to stat. Oh, and it's, nope, actually, I won't say that. So let's go here. We'll go to regression, go to simple linear. Now, if you want to try to mess with other regressions, you can, but in this class, we just learned about linear regressions. So you go to simple linear, and now you have to tell it, it matters which one is the x variable and which one is the y variable, because you can do it either way. You can like switch it around if you want. So I could make the x variable height and the y variable shoe size, or I could make the x variable shoe size and the y variable height. If I was going to turn in a project for a statistics course, I'd do it both ways. Since it only takes a second, I'd do it both ways and see which one I prefer, which one makes more sense to me, and which one helps me understand the data better, which one contributes more to the narrative that I'm trying to construct about the data that we're putting together. So in this case, yeah, we can do it this way. Okay, where optional, you've got some stuff. Don't worry about hypothesis tests yet or confidence intervals. We're not really getting into that yet. You'll do that later. Prediction of y. So remember how I told you we can use that regression line to make a prediction? Maybe you have a prediction that you actually want. Well, you can put that x value in here. So let's see. Ours was shoe size. So what if I wanted to make a prediction about a shoe size? So someone who is size 10, what is the expected value for the height of someone whose shoe size is 10. So I'm putting that predicted value in there. We don't need any of those. We don't need any of those. Again, your x-axis label, y-axis label, title. It only takes a second. Fill those in, all three of them. If you have one of those empty, you're leaving behind some easy points. So fill those in. Okay, let's compute. Okay, so now I get a bunch of, I don't know, this is like a bunch of confusing text. I don't want to read all that. It's helpful, right? A lot of this you don't need, but a lot of this is helpful. And again, he goes over this in detail in that video. So if you want to just look at the YouTube video, you can quickly figure it out. Now the p-value, we haven't really talked about p-values much so far. So for now, you can kind of interpret that or ignore that. Things that you need. So here's your R value. Right, there's your R value right there. Our R value is 0.68234214. Now, this is just data I made up. I just made it up before class so that we'd have something to talk about. But that's a made-up value. You've got your R squared value, which comes up a little bit in this class, but you can decide if you want to include that in your project or not. But definitely you should be mentioning the R value. And the other thing is, sorry, they're doing yard work outside, of course. This is your regression line right here. And you might go, well, wait a minute, where's the X and Y? They're using the actual variables that you used instead of the X and Y. So your shoe size is like your X, because remember, we put shoe size on the X axis. Height in inches, that's the Y value. So this is really Y equals 61.414076 plus 0.6914913 X, right? Where X is our shoe size, Y is our height in inches. So there's your regression line right there. Now, if you look right here, that's my coefficient that's on X, right? 0.6914934. That's my slope. Remember, that's my rate of change. So what this is telling me, here's my interpretation. As shoe size increases one unit, then I expect the height of the person to go up by 0.6914934 inches, right? Because we have our units right here. Remember how I labeled my units? This is a thing that happens in chemistry all the time. There's like, and in math, people will drop the units and they find these problems to be super hard, right? And then as soon as they include the units, the problem becomes super easy. You literally have problems like that in chemistry where the whole thing is just matching up units and getting things to cancel out. Some of you probably remember doing that when you're doing conversions in chemistry. You line things up so your units all cancel. And then the problem is super easy. If you try to do that problem without using units, forget it, right? It's just a big mess. So that's why we always want to put units in here, because then I'm not confused about, well, how did we measure height? Was it centimeters? Was it inches? What did we do? This tells me for each change in one shoe size, this is the change in height we expect to get. Now see these arrows at the bottom? If I click this one, it takes me right over to my regression line, and I didn't put in labels. It sort of has height in inches and shoe size in US already for me, which is good. You probably want to put a different title on here, so a nice good title. But see, we've got that line going right through here. That line going through there. And it's a decent representation, right? But it's not great. So that R value being kind of low tells us this line will be predictive, but it's not, like, I wouldn't really rely on it. Like, it gives you a ballpark of what someone's height's going to be given shoe size, but you know, don't bet on it. Don't go out and buy clothes for them based on their shoe size, because you're going to get we see a pretty good variation here in this variable. But here we've got our graph. You can save that and print it out however you want. We can change the title right from here, it looks like. So this would be, you know, whatever this is. We make this up. So American women shoe size versus height, or whatever it is, right? And then you've got, you know, whatever it is that we've measured. You put it in there as your title. You've got your units and your labels here. So everyone knows exactly what we're looking at. You go, okay, there's a reasonable relationship here. There's an overall behavior, but it's not like super strict. Okay. And then you've got all that taken care of. You can go through. And so all the stuff that you're learning about in the lessons on regression and correlation, by doing what we just did, you've got all that available to you right here in StatCrunch, right? And then later on, when we understand p-values at a better level, when we're doing hypothesis tests and confidence intervals and all that kind of stuff, you'll understand more of what's down here. Right. Oh, and then we had, here's our predicted value at the bottom. Remember I put in 10 and I wanted to know what would the predicted height be for someone who has shoe size 10? Well, here it's giving us the prediction, 68.328989. We can expect the person to be somewhere in this neighborhood, but again, they might be a few inches taller, they might be a few inches shorter, but we probably would not see someone who's, 50 inches tall or something with a shoe size of 10. Right, we wouldn't expect it to vary that much. One thing you should be aware of, the difference between interpolation and extrapolation. Interpolation is much more reliable. It's when you're making a prediction about a data point that lies inside of your data set. So like for us, that would be somewhere between 8 and 14. If we wanted to make a prediction about a shoe size of, say, 12 and a half, we'll see how we're missing that value at 12 and a half. So we could go back and we could make a prediction. Interpolation, which is what I'm talking about, is more reliable than extrapolation. Extrapolation is where you start making predictions about things outside of your data set. So if I wanted to make a prediction about a shoe size of 5 or a shoe size of 18, or what does Shaq wear, like 22 or something like that, we wanted to make a prediction about that. It's probably the further you go in your extrapolation, the less reliable your prediction is going to be. Whereas with interpolation, you can kind of see, by looking at the graph, you can get a sense of how reliable that prediction is going to be. Okay, so just a little detail there that you want to keep in mind about those things. Okay, so let's see. So remember, you have coming up to, that's not right. Oh, October 12th is not super far away either. But so you can do your project correlation piece, but also remember you've got coming up, really you've got 3 things for the project coming up. This is the right one, right? This is 18 week, yeah. So you have 3 things for the project coming up. They don't take terribly long, right? I wouldn't think you should need to spend more than like 20, maybe the project visuals, because you're probably going to want a bunch, right? You're showing a video. You're probably going to want to show people a bunch of visuals. So if you're making a 15-minute video, you probably want to have a few visuals for each question that you're creating. Just makes for a better presentation. Histograms, dot plots, maybe dot plots, pie charts, stuff like that, whatever you think is necessary. The survey question summaries, these are pretty straightforward. That should probably take you 10 minutes to do that. Project visuals take a little bit longer. Maybe spend 30 minutes on that. And then get together with your group and compare. And then you've got the correlation stuff coming up that we just went over that, right? So that shouldn't take terribly long, but it might take you a little while since you're still kind of learning about it. But I just showed you how to make the chart, put the line in there, evaluate your R value, all that kind of stuff. Okay? Okay, so in just a moment, I will shut down the YouTube stream. Anyone who wants to chat with me about whatever you were thinking about that's school-related, please come talk to me in the Zoom meeting right now. Actually, I think today's, Thursday? So I actually have office hours today. So, and I'll talk to you after class any day anyways, whether it's office hours or not. But come on in, ask me questions. And otherwise, I will see you next week. Don't forget those things that are due. Okay. All right. Thanks, everybody.